question on B.
On B?
You said zinc 2 plus was stable in water, but it has a voltage of negative 0.76, and it doesn't fall in between the 1.82 and
zinc plus, okay, the ionic form, zinc is not going to be, in other words, that's the ionic form. What's it going to do? Is it going to be oxidized by water? That's a whole different, we don't have the reduction potential, that the information is not available for the reduction of some zinc higher ionic form. Zinc is found in +2 or 0. So if there was a zinc +4, for example, we'd need to know its reduction potential. We don't have that.
So we only know them for
So,
the elements.
Yeah. Well, what we know when we're talking about the ions, if we're talking about them being oxidized by the water, that has, then it would have to be the reduced form is the one that's oxidized. That's the point. In other words, it's the reduced form. The reduced form of the zinc couple is the zinc. Not zinc +2 is the oxidized form. That's the product of oxidation of the zinc, right? So when I have the couple, it's like this is the oxidized and this is reduced. This is the oxidized form and the reduced form. So what is oxidized when we place it in water? The reduced form. The reduced form is the one that's oxidized. The oxidized form is the one that's reduced. Okay? Okay, and so the zinc +2, in order for it to be oxidized, it's going to have to go to a higher oxidation state. And that information is not available. And plus, zinc isn't found. It's found in +2 oxidation state. It's not found in higher oxidation states. But if you could make it that way, we'd have to have that information to find its reduction potential, and it's going to be much higher. It's going to be way up there.
But in relation to the graph, or how do you know that it's stable?
Well, because it's okay. Is it stable towards being oxidation? Towards oxidation. I'm looking at the reduced form when I'm talking about oxidation. When I'm talking about reduction, it'd have to have a reduction potential for the oxidized form. It has to be greater than 1.882. Yeah. And so, you know, that this is minus 0.76 volts. That's definitely not greater than 1.82. Okay. So it's not going to be, this is not going to be reduced by the water. And it's not going to be, we don't have any information, enough information, but I'm willing to bet you, if I could make zinc in a higher oxidation state, the reduction potential is going to be much, much greater than 1.82. It's going to be way up there. Remember the cobalt couple? That was, in order for it to be, if I could get the zinc 3+ to exist, it wouldn't be stable in water. It probably would have a reduction potential that's very, very high. But it's not found. Okay. So we don't have to worry about this in terms of it. We're concerned about whether this is going to be reduced because it's the oxidized form. So I don't need to worry about that. It's stable in water with respect to being to being reduced. If I have an ionic form on the right-hand side, I have to worry about whether it's going to be stable with respect to being oxidized. Because the reduced form can lose electrons. It's got electrons to give up. This can gain electrons and be reduced. This can lose electrons and be oxidized. The problem with electrochemistry is a lot like doublespeak, isn't it? Yeah. It takes a little while to get used to this language. You have to really slow down. Okay?
That's the oxidizer, but it's the reducing agent.
Yeah. The oxidizing agent is reduced, the reducing agent is oxidized, and it's like the party of the first part and the party of the second part. I don't go to parties like that anymore. Yes?
It's kind of an understanding check. If the question was which ions would be reduced by dissolving oxygen in water, the bromine ion would.
Well, okay, reduced by, okay, well, the reduced form of oxygen is water. Okay, so, okay, now, okay, so we're back to, did that answer your question about the other ions, or not? You still having trouble with it?
Yeah.
Okay.
Somewhat. It's okay.
Well, no, it's, let's talk about it a little bit. The main thing is, I guess I should put this generic statement up here, that the E, the reduction potentials, is of the oxidized form on the left and the reduced form on the right. And so this describes the amount of, or the work that is done adding an electron to the oxidized form. The reduction potential takes the oxidized form and adds electrons to it. It's all these, you'll note all these equations are written as reduction half reactions. So we write everything as a reduction half reaction. And then, so if I'm worried about something being oxidized, then I have to have, I'm more concerned about the reduced form. That's the information I get is from the reduced half of the couple. If I'm worried about something being reduced, I look at the oxidized form. And so when in those particular questions, I was asking about which ions are stable in water, which ions are going to be either oxidized or reduced by the water. And there weren't, well, the only one, well, wait a minute, they were all stable. Yeah, they were all stable in water. There wasn't a single one that was unstable. The only one would have been, I could have thought it would have been the cobalt 3+, and that wasn't in that field.